The world has definitely come to a fast pace in terms of daily living, but what is the fastest speed that everyone in the universe can go? Can we go beyond that? That's what we're going to find out in today's episode. If you watch the animated series of Pokemon, it's impossible to have missed the following lines. Team Rocket, blast off at the speed of light. Surrender now or prepare to fight. Said, of course, by the ragtag duo of wannabe antagonists of the show, the Team Rocket. If you're like me who thinks a lot about stuff I hear, you might have pondered about that penultimate line. Blasting off in the speed of light? Is it really possible to get something to move to the tune of the fastest speed of the universe, the speed of light? Well, we know that there aren't any intergalactic police to monitor whether or not we're going beyond the universal speed limit. But what exactly is preventing us from going beyond this anyway? These are two heavy questions that we will answer today, but I want to know what you guys think about these. Do you think we can go faster than the speed of light? Or do you think it's pretty much impossible? Let us know in the comments section down below. I know a lot of you already have the right answer to this, but let's play the devil's advocate here for a bit, shall we? So how about we define first the speed of light so that we don't get all confused by the variances? First and foremost, at least in the spirit of this video, when we say the speed of light is constant, the speed of light that we are talking about here has two main characteristics. First, this is the speed of light in uninterrupted space, or vacuum. Second, we are talking about the speed of light in an unchanged space-time, or a flat space-time. Basically, how we would normally see space, absent from the effects of other factors. In case this is the first time you are hearing about all this, the speed of light is estimated to be 299,792,458 meters per second, or around 3 times to the 10th 8 meters per second. If you're not a fan of the metric or residing in the United States, that's around 186,282 miles per second. One of the earliest experimentations leading to the concept of the speed of light being constant is done by one of the biggest names in physics, Galileo. This is how his experiment went. He and an assistant, which we will name Vinny for the sake of the story, would stand at the top of 2 hills carrying each a light source, which would most probably be a lamp. Considering the time of the experiment, the lamp would be completely covered with a shutter to effectively flash light. Galileo would then remove the shutter, which would be the signal for Vinny to remove his as well. Then Galileo would record the time he saw the flash. He then repeated the same experiment and found out that no matter how far he went, he records the same time of flash. At that point, his conclusion was that light must either be really, really fast or that it is constant, to which the latter sounds extremely ridiculous that time. Why? Stay tuned to find out. And come 1676, Ole Romer verified that the speed of light is indeed constant by observing the moons of Jupiter. However, this fact gets highlighted hundreds of years later when a brilliant mind named Albert Einstein came up with his paper in the Theory of Relativity, one of the most important and groundbreaking publications in physics in the history of mankind, so far at least. To be able to understand his point, we need to first understand how relativity is defined in a classical sense. For instance, say that you are riding a train moving at a constant speed. Let's call that speed v. And one friend of yours is looking at you outside of the train on the platform. This friend of yours has a really fantastic eyesight, so any little movement of yours he can see absolutely clearly. Okay, at this point, let's say you decided to be playful. You wanted to test his vision. So what do? You fished out something from your pocket and then threw it towards the front of the train. Say this object that you threw has a speed that we will call s. Take note that s is how you think the speed is going. Your friend on the platform acknowledging your action will see it differently. To his perspective, the speed of the object is v plus s. This is classical relativity. When conditions in the universe are pretty much static, for lack of a better word, we are bound to see these events. So okay, what exactly makes Einstein's take on relativity more special than the classical one? In his theory, he stated that it is not really because of the staticness of the universe that gives us these laws of physics that we observe. According to him, as long as our frames of references are moving at a constant velocity, we expect the laws of physics to stay the same, whether we're in a room or in a train moving at the same speed throughout its trip. In a spacecraft, we expect that we are restricted by the same laws. In his paper, he categorized these frames of reference to be inertial, as a nod to the law of inertia by Newton. Remember what that says? In a very short summary, it says that all objects tend to keep their state of motion, whether it be moving or non-moving, until it is interrupted by an outside force. Pretty neat, right? Okay, before moving any further, I'd like to know if you're enjoying the show so far. Are you excited? So how does inertial frames of reference relate with the consistency of the speed of light? Let's go back to the train, you and your friend. Let's make everything cosmic and absolutely ideal for all intents and purposes. The materials don't experience stress. Your condition inside the train doesn't change. Your friend's vision is unadulterated, etc. Every condition we placed is achievable. Let's agree. Your friend is standing on a cosmic platform in space, well protected with astronomical gear, of course. And now he's looking at you, sitting inside a train, accelerating at the speed of light. Now you're sitting quietly on the train and you realized you gotta pee, and the toilet in this cosmic train is near the driver for some strange reason. So you gotta act on this. You stand up, you try to semi-sprint to the front of the train. Now let's go to your friend with a hawk eye. What does he see? If you recall classical relativity's approach to this, whatever speed your friend sees you move to will eventually become more than the speed of light, right? So did we do it? Did we violate the laws of nature? The answer is no. Here is where Einstein's genius really shines brightest. According to him, if you actually move at the speed of light, you will experience three things: a compression of length, slowing down of time, and a severe increase of mass. So if we go back to your friend on the platform, here's what he'll see. As you approach the speed of light, he will see that you are moving extremely slowly until you stop, as you are experiencing time dilation. Moreover, the train will compress in length shorter and shorter. Eventually, to your friend on the platform, you'll disappear suddenly, since you practically have zero length. No length, no time, and infinite mass. I bet at this point you can already see how this would be problematic, right? To get something to move with infinite mass, you need an equally infinite amount of energy. This violates conservation laws, not adding the problem of what having zero time means, as that is a violation of thermodynamic laws. And this is not purely theoretical too. You can get the math done and see that whatever you do, your equation will end up with c, the speed limit. This is a groundbreaking statement, as back before Einstein, the consensus that different frames of reference will have different laws of physics. Our dear Albert crushed all of that with a single blow, by defining the speed of light as a universal constant. So I'm sorry to those who have thought we can travel faster than the speed of light, but the answer is a resounding no. However, there are some glitches in the universe to this rule. A ray of hope? Let's find out. For instance, I'm pretty sure you've heard sometime around 2011 that neutrinos may have possibly gone beyond the speed of light. However, this is later found out to be a bad reading by instruments in the Opera project, so let's scratch that one out. Another example is something that we call Cherenkov radiation. It works this way. The speed of light retains its value as long as it's going through a vacuum. However, when it goes through a transparent medium, it slows down. This phenomenon is more popularly known as refraction. So knowing this, you can go faster than the speed of light by firing a charged electron that would be faster through the material. Oh, and the electron emits radiation, by the way. Hence the name Cherenkov's radiation. But we didn't technically go beyond the number we aimed to at this approach, didn't we? The speed of the electron is still below 300 million meters per second. So what else can we try? There is also quantum entanglement. This is an extremely complicated topic to talk about, but in essence, and I would even add this description, I will say severely oversimplifies it. So we can sort of set up a pair of particles such that their properties are complementary with one another. Let's say this property is a spin, for instance. We can set up two particles such that one has a spin up, while the other a spin down property, and have these particles entangled in a way. What that means is that, say I take the spin down particle to another galaxy. If I change that property to spin up, that will instantaneously affect the other particle to reverse its spin. If it happens that quick and that instant, then it has to be faster than the speed of light, right? Einstein, back at it again, labeled this phenomenon as spooky action at a distance. No one knows why this happens, but this is certainly an observable phenomenon. Does it bring us closer to beating the speed of light? We don't know yet. Okay, what else can we try? How about another suggestion from Einstein? If you're a fan of science fiction stuff, you definitely have already heard about wormholes. But in case you haven't, these are effectively points in space-time which serves as some kind of shortcut. Say for instance we have 2 points in a paper which we drew at the top and bottom. If we want to connect these two, we would draw a line, right? But if we can fold the paper such that these 2 points touch, then we went faster. Again, this is another cheat, as we needed to violate the space-time on which light travels. But hey, if we can get this running in reality, right? But to top off the show, let's talk about something that's actually faster than the speed of light that we have observed to occur in nature. According to observations done by astronomers, some galaxies are moving away from us at rates that are way faster than the speed of light. However, before you get too excited, let me tell you that this is not entirely the whole story. I know. I have that habit of building you up and then killing your excitement. I hope you can forgive me for that. I just want to be precise and sound with the information that I share with you guys. So okay, this isn't it, but how come astronomers observe this to be happening? Let's take a hint from the wormhole instance. Remember how we practically cheated by, instead of racing with light, we folded the running field instead? This is pretty much a parallel variation of that. It's not that galaxies are moving way faster than the speed of light. Remember, if something does that, there are consequences, such as slowing time, shrinking length, and blowing up mass, but we don't see that happening. What's actually observed here is the expansion of the universe. This is what's moving faster than the speed of light. To visualize this better, say you made a paper boat and you carefully place that boat on a river. You try to be as careful as you can, as you do not want to add force to it such that it moves. However, upon placing it there, it moves anyway. Why did this happen? Because the stream of water itself has an initial speed already. Remember classical relativity? You thought we already moved on from that, huh? So basically, the galaxies that we see moving away are like the paper boat, and the river is the universe. And let me add some bad news relating to that. Since the universe is moving faster than light, there will come a time where the light from these galaxies will no longer reach us, and we wouldn't be able to observe anything else from the universe anymore. We would literally feel alone in a very, very dark place called the universe, until something finally concludes our existence. Kind of a grim note to end with, huh? Let's avert that a bit. These are things that are established, but I want to know what your thoughts are with this matter. Leave us your suggestions below on how we can travel faster than the speed of light.